Okay, we are now moving out of Chapter 2 into Chapter 3 in Precalculus, into Section 3.1. So we're getting away from polynomial and rational type functions at this point, and we're moving into what are called exponential functions. Okay, so we want to make sure you know how to evaluate exponential functions, graph them, evaluate functions with what is base E, I'll explain that in a little bit, and then use some compound interest formulas. Okay. So first of all, what is an exponential function? An exponential function is any function that looks like f of x equals b raised to the power x. So b is a positive constant, and b is greater than 0, so it's a positive constant. But it's not 1, because 1 to any number is just 1. So we think of 2 to the x, or 3 to the x, or 4 to the x, or any number actually, just a positive constant, just can't be 1. And then x is any real number. Okay. So I can't really show you on here, but just make sure you know how to evaluate these types of functions on your calculator. Most calculators have a b to the x button, or it'll say y to the x or x to the y, but basically, and then you put in the numbers in the way they need to go in. So if anybody has trouble with that, send me a email or a message through Canvas, and I'll try to see if I can find a video for you on that. But if you Google your calculator and how to evaluate an exponential function, I think you'll be able to find something on that as well. Okay, so example, exponential functions, 2 to the x, 10 to the x. By the way, it doesn't have to just be x, right? But as long as it's x with plus or minus a constant, then it works. Okay, so it's just like if I have f of x or I have f of x plus 1, remember what f of x plus 1 would do is shift it to the right by 1 unit, right? Okay. No, sorry, shift it to the left by 1 unit. Shift it to the left by 1 unit. So this would shift 3 to the x to the left by 1 unit if I were graphing it. Okay, so functions that are not exponential functions, x squared, that's a polynomial, right? 1 to the x, we don't ever have a b of 1. Minus 2 to the x, because you can't have a negative number. It has to be a positive constant, because minus 2, if x is like 1/2, that means say take the square root of minus 2, which we know we can't do. So this has to be a positive constant. That is not an exponential function. And then, of course, x to the x is not an exponential function. This should be a positive constant to the x. So these are examples of exponential functions. These are examples of functions that are not exponential. Okay, so example. Let's say we have this function. This is a constant 42.2 times a positive constant to the x power 1.56x. So this is an exponential function. It just has a constant in front of it. This is a positive constant raised to the power x. And this actually models something. It models the average amount spent, f of x, in dollars at a shopping mall after x hours. So this is done after collecting data, fitting it to a curve. There's lots of higher level math than that, but somebody collected data, observed people, how much they're spending, or collected receipts from stores and how much people are spending. So after spending so many hours in a shopping mall, this is the amount of money that can be spent there on average. So what is the average amount spent to the nearest dollar after 4 hours? And so the number of hours is x, so you're plugging in 4 for x. So you would have to plug this into your calculator. You'd say 42.2 times, and then you would need the b to the x button, so you'd have 1.56, and you hit the b to the x, hit 4, hit enter, and then that would come back. Again, play with your calculator. Make sure when you do this calculation, you get this number. This is correct, and you'll know if you're doing it correctly. 249.92566, or since I'm going to the nearest dollar, $250. If I went to the nearest cent, I would say 249.93 or $249.93. But I asked to the nearest dollar, so we say $250. All right, so graphing exponential functions. The first thing you should think about when you're graphing exponential functions is the following. If b is greater than 1, then an exponential function looks like this. By the way, they always pass through the point 0, 1, because when x is 0, what's any number raised to the 0 power? That's 1. So they always pass through the point 0, 1. B to the x looks like this. It's reflected about the y-axis if b is between 0 and 1, not including not including 0 or 1, of course, but between 0 and 1. So notice that the domain of any exponential function is minus infinity to infinity. X can be anything. You plug any value of x in, but the range is always positive, 0 to infinity. It never reaches 0. There's no way to get 0 when I plug x in here. But it can get closer and closer to 0 if b is greater than 1, as a horizontal asymptote of y equals 0 as x approaches minus infinity. If b is between 0 and 1, has a horizontal asymptote of y equals 0 as x approaches positive infinity. And then just remember transformations of functions in general. For example, if we want to graph f of x equals 2 to the x minus 1 plus 1, think about what this is. This is shifting 2 to the x, so this is like f of x minus 1. That shifts 2 to the x 1 unit to the right, and then adding a constant means it goes up or down the y-axis. So plus 1 means you would shift it 1 unit up. So the easiest thing to do is to get some points for just 2 to the x and then shift it appropriately to get 2 to the x minus 1 plus 1. So some points for 2 to the x, plug in x equals 0, 1, 2, 3, and then let's plug in minus 1 and minus 2 so we can see what it's doing on either side of the y-axis. So when x is 0, first of all, that was silly because I know it would always be 1. So these open circles here are plotting 2 to the x, because that's not the function we want. We're going to shift it. Okay, when x is 1, 2 to the 1 is 2. So when x is 1, 2. Right there, that's there. When x is 2, 2 squared is 4. So when x is 2, 2 squared is 4, this open circle. When x is 3, 2 cubed is 8. So here's x equals 3. 2 cubed, 2 to the 3 is 8, that open circle. When x is minus 1, 2 to the minus 1 is 1 over 2 to the 1, or 1/2. That's right here. X is minus 1, y is a half. When x is minus 2, it's 2 to the minus 2, or 1 over 2 squared, which is 1/4. So right here, when x is minus 2. And then I know the basic shape, so I know I can draw in this dotted line to kind of go through these open circles, and that's 2 to the x. So then to get 2 to the x minus 1 plus 1, I shift 2 to the x 1 unit to the right. This is like an f of x minus 1. Plus a constant means shift it up or down the y, so plus 1, shift 1 unit up. So I take every point, shift it 1 unit to the right, 1 unit up. Take this point, 1 unit to the right, 1 unit up. This point, 1 unit to the right, 1 unit up. This point, which was on that curve, 1 unit to the right, 1 unit up, right here. This point, 1 unit to the right, 1 unit up, boom. This point, 1 unit to the right, 1 unit up, boom. And then I have those filled in dots that'll connect the curve, and there is 2 to the x minus 1 plus 1. All right, let's say we want to graph f of x equals e to the x minus 2. So this will shift the function e to the x 2 units down the y-axis, right? Subtracting 2. So I need to evaluate e to the 0. So actually most calculators have an e to the x button because e to the x is a very common function. So first of all, I don't know if you remember e, but e is called Euler's constant. It's like 2.718281827. It's one of those irrational numbers that shows up all over the place in nature, sort of like pi does, so it gets its own special name. It's actually called the natural base. Euler was the first mathematician to work with it. And so e to the x is called the natural exponential function. So most calculators actually have a button for e to the x. So you can plug in e to the 0, e to the 1, etc. And you get these open dots. Shift every point 2 units down. So instead of having y equals 0 or the x-axis be the horizontal asymptote, we now have y equals minus 2 as the horizontal asymptote. Every point is shifted 2 units down, 2 units down, 2 units down, 2 units down, 2 units down. Okay, so that's e to the x minus 2. All right, formulas for compound interest. These come up, these are interesting formulas, some financial mathematics that we can do once we know exponential functions. So if we're talking about, here's the formula. After t years, the balance A in an account with principal P, principal is the amount of money you put in it to begin with, and an annual interest rate of R in decimal form. So let's say your interest rate was 6%, then the decimal form of that interest would be 0.06, is given by the following formulas. So for n compounding periods per year, that means like the bank will tell you we compound monthly, or we compound annually, or we compound semi-annually, etc. That's how many times per year they do the compounding. So the n is the number of compounding periods per year. The formula is this: A equals P, the principal, so the amount in the account is the principal times the quantity, 1 plus the interest rate in decimal form divided by the number of compounding periods, all raised to the quantity, NT, the number of compounding periods per year times the number of years. So if they say compounding annually, it means they only compound it once per year, so n is 1. Compounding quarterly, right? That would mean they compound it every 3 months, or 4 times. Compounding monthly would be they compound it every month, or 12 times per year. Compounding daily, compound it every day. There's 365 days in a year. I didn't put semi-annually, but semi-annual would be n equals 2. Now, a lot of places do continuous compounding. If it's continuous compounding, then that means n is approaching infinity. Now, there's some mathematics behind there. It's actually calculus to get to here. Okay, so you won't be able to do that. What you need to do is push the I believe button for me a little bit, that it's this formula, A equals P e to the RT. Okay, so it's the principal times our natural base raised to the RT, interest rate times the years. Because the number of compounding periods approaching infinity, this formula, in the limit, as n we're getting bigger and bigger and bigger, going to infinity, becomes this guy right here. So, we want to see what's better. Find the accumulated value of an investment of $8,500 if it is invested for 3 years at an interest rate of 4.25% and the money is compounded monthly. Okay, so we have an interest rate of 4.25%. So in decimal form, that interest rate is 0.0425. Compounded monthly tells me that n, the number of compounding periods per year, is 12. The principal that you initially put in there is 8,500, so there's your P, 1 plus the interest rate in decimal form divided by n, the number of compounding periods, all raised to n times t, the number of compounding periods, times 3, the number of years. You got to be able to plug that all into your calculator to get $9,653.70. So try that. Make sure you know how to use your calculator to get the right number. In this fourth example, we want to find the accumulated value of an investment of $1,200 if it is invested for 6 years at an interest rate of 6% and the money is compounding continuously. So once it becomes compounded continuously, we just need to know the principal and the interest rate and the number of years, because it's P e to the RT. Principal's 1,200, E is our natural base, R is 6%, so in decimal form is 0.06, T is the number of years, so it's 6 years. You should be able to use your E to the X button, do this to see that that's $1,720.